We are very pleased to have as our final speaker, Max Metlitski from MIT. Max received his undergraduate and master's degree from University of British Columbia in Vancouver. And even at the time he was writing influential papers, I remember reading his paper on anomalous currents when he was in UBC, and then after graduating from UBC, he moved to Harvard University, from which he got his PhD in 2011, and then he had a postdoc in Calvi Institute at Santa Barbara till 2015, and he had a faculty appointment at Perimeter Institute in Waterloo in Canada. And then finally, he moved to MIT and started as an assistant professor in 2017. So in addition to his very influential work on strongly correlated systems and topological phases and so on, he also is the recipient of the Kimmel Award in 2013, as well as the New Horizons Prize in 2020. And we are very pleased to have Max as our final speaker. And Max, please take it from here.
Thank you very much for the invitation and the very kind introduction. I remember a couple of recent progress in many body theories conferences, I think in Ohio and Rostock. They were really great. Can people hear me well? Yes? Oh, thank you. Yeah, and please, if you have questions, please feel free to ask them during the talk. I think that's more fun. Yes, so I'd like to talk about some work done last year, and there is going to be a new updated version of this paper on arXiv soon. Now, I'm going to talk about a rather old subject, boundary criticality in the ON model, but I'm going to try to convince you that some actually really basic questions were not properly understood in the old days, and there's been some progress on that recently. I should apologize from the beginning that actually I'll mention some quantum models, but actually most of my talk is going to be about classical StatMech models. Even there, it seems like things are not settled. Okay, so the subject of my talk is boundary criticality. So what is boundary criticality? Well, imagine that you have a bulk system that's going through a phase transition. And let's say the phase transition is described by a conformal field theory. And now suppose you want to study the system in the presence of a boundary. So maybe you want to compute correlation functions involving operators on the boundary and also operators in the bulk. And there are a couple of points that can be made right away about this problem. First of all, the boundary criticality is really in general different from the bulk criticality. For instance, the spectrum of scaling dimensions of boundary fields is distinct from that in the bulk. The second point is that the boundary conformal field theory is not unique. For a given bulk critical point, there can be distinct boundary universality classes. And then you can tune between these boundary universality classes by changing the details of the Hamiltonian near the boundary. Loosely speaking, there can be more than a single boundary condition in the infrared. Okay, so like I said, this boundary criticality is really an old problem, going back to classical statistical mechanics in the 70s and 80s. But there's been some resurgent interest in the field lately, and this I think is driven from at least two directions. First direction is kind of, in general, improved understanding of conformal field theory in dimension larger than 2, driven particularly by the conformal bootstrap, by successes in conformal bootstrap. And the second direction is from quantum matter, and in particular from the physics of topological phases. So we know that many topological phases, while gapped in the bulk, host protected gapless boundary states, and that has driven interest in boundary physics in general. Now, for a long time, it was thought that for these phases, the existence of the bulk gap is crucial for the protection of the boundary states. However, it was later realized that sometimes, even when the bulk gap closes, the boundary survives in the boundary state, the non-trivial boundary state survives in some form. Then it falls squarely in the domain of boundary criticality, because you have a bulk gapless system, and you're studying the boundary behavior. In particular, one very specific setup is that you have a symmetry-protected topological phase in the bulk, and you drive it towards some symmetry breaking transition, and sometimes at the critical point, the surface state survives in some form. I think this was first noted by Tarun Grover and Ashwin Vishwanath in some examples, but there's been actually a lot of literature on this lately. And towards the end of my talk, I will mention some quantum models of this flavor. However, like I said, most of my talk is going to be about classical StatMech. In fact, about one of the simplest StatMech models out there, a textbook model, the classical ON model. So what is the classical ON model? Well, take classical spins, just n-component vectors of unit length, sitting on sides of a hypercubic lattice, and couple them with the nearest neighbor coupling Kij. Now I'd like to consider this model in the presence of a boundary. So kind of think about a semi-infinite system. And for spins sitting on the boundary, let this coupling be K1. And for the rest of the spins, let the coupling be K. And I want to study the phase diagram of this classical model as a function of two parameters, temperature and the ratio K1 over K, the ratio of the surface spin coupling to the bulk spin coupling. All right. Well, what can be said? Well, first of all, this model is going to have a bulk phase transition as long as it's above the lower critical dimension. It's going to have a bulk phase transition at some critical temperature Tc, where the spins in the bulk order. So what happens in the presence of a boundary? Well, here is the accepted phase diagram when dimension d is greater than 3. We will come back to what happens in d equal 3 later. D equal 3 will be the interesting case where things are still not settled. By the way, d here always refers to the bulk dimension. All right, so if d is greater than 3, then you open up a textbook, and here is the phase diagram, including the boundary. And what are the phases? Well, if this surface coupling K1 is not too large, then what happens is that the boundary and the bulk order at the same critical temperature Tc. This is known as the ordinary boundary universality class. Now, if you make K1 large, then what can happen is that the surface can actually order before the bulk orders at a high temperature. That's this green line here. And then the surface transition, well, is just the bulk still has a finite correlation length here. So this is a pure surface transition described by the d-1 dimensional OM universality class. So then we go from a phase where both bulk and surface are disordered to a phase where the surface is ordered and the bulk is still disordered. Now, the more interesting transition is one where the bulk orders in the presence of a surface order. So there is still there are still singularities at this phase transition, and it's known as the extraordinary boundary universality class. Finally, there is this multi-critical point separating the ordinary from the extraordinary region at the bulk critical temperature, and this is known as the special transition. All right, so this is the accepted phase diagram when dimension d is greater than 3. Now, and note this is the phase diagram in the absence of any symmetry breaking field on the boundary. One can also consider turning on a symmetry breaking field on the boundary, and then it's believed that the model admits just a single boundary universality class, which is known as normal. Same universality class for all values of the surface coupling K1. And the interesting fact is that if the bulk dimension d is greater than 3, then it's believed that morally this the extraordinary transition, which takes place in the absence of any symmetry breaking field on the boundary, is the same as the normal transition. Essentially, it doesn't matter whether you break the symmetry on the boundary explicitly or spontaneously. Once you have a finite surface order parameter, you have the same universality class of the transition. This is easiest to understand for Ising spins, which are kind of rigid, but it's also believed to be true for spins with ON with n greater than 1. Essentially, it's believed that the fluctuations of the Goldstone modes associated with this surface, with this ordered surface, decouple from the bulk fluctuations at the extraordinary transition as long as d is greater than 3. All right, so this is the lore. Now, what will be the subject of my talk will be what happens when the dimension d is equal to 3. And here we'll see there are some surprises. Well, first of all, if we are talking about Ising spins, then the same story holds for dimension equal to 3, same phase diagram, same kind of phase transitions. The situation is more interesting for n equal to 2, right? So xy spins. So here we no longer can have the system can no longer support true long range order on the boundary for temperature greater than the bulk critical temperature, right? We know that strictly in 2 dimensions there is no true long range order for xy spins. However, you can have a quasi long range order on the boundary. So the phase diagram still has the same topology as before, but this corner of the phase diagram is a phase where the bulk is disordered and the surface supports quasi-long-range order. And then this transition is just a standard 2-dimensional Kosterlitz-Thouless transition, this green line. So that's understood. But what about this extraordinary transition? What happens as the bulk orders in the presence of this surface with quasi-long-range order? What's the nature of the extraordinary transition? So it turns out that this question was not settled in the literature before my paper, and actually there was not a lot of discussion of it. really the only discussion I could find is in this numerical paper by Deng, Blotta, and Nightingale. It's a Monte Carlo paper, and one scenario that they put forward is the following: that well, above TC, the surfaces doesn't have true long-range order, but maybe right at TC, the surface does order. Well, that would essentially mean that the surface order parameter has a jump across TC as shown here. And this picture was roughly consistent with their Monte Carlo data. Well, this sounds a little funny, but actually it's quite hard to shoot down immediately. Why? Well, we know that for t greater than Tc, the Mermin-Wagner theorem prohibits existence of true long-range order on the boundary. But right at Tc, in some sense, all bets are off, right? Because if you think about integrating the bulk out right at Tc, the bulk fluctuations are going to induce power law interactions of the boundary spins. And we know that when we have power law interactions, in general, the Mermin-Wagner theorem no longer applies, and you can actually have true long-range order even in 2 dimensions. So this scenario is hard to shoot down, kind of from general principles. Nevertheless, I will show that it doesn't occur. Instead, what happens is the following. Along this extraordinary line, the 2-point function of the boundary or the parameter takes the following form. It decays as a power of logarithm of the separation of the 2 spins. So it decays very, very slowly, but nevertheless it does go to 0 as the separation goes to infinity, so there is no true long-range order at the bulk Tc. So the boundary is almost ordered, but not quite. Another way of looking at this is that if you approach the bulk transition starting in this phase with quasi-long-range order, then the Latinger parameter of the stiffness of the surface diverges logarithmically. I remember this Latinger parameter is what controls the power law of the 2-point function. So I term this the extraordinary log universality class, boundary universality class, to distinguish it from the true extraordinary universality class that one has, say, for Ising spins in 3 dimensions, or for other ON in d greater than 3, where the spin-spin correlation function at infinite separation really goes to a constant. All right. So that I'll explain where this behavior comes from shortly. I'll give a renormalization group proof of this fact. All right. So this is n equal to 2. What happens for n greater than 2 in 3 dimensions? Well, we know that when t is greater than tc, we essentially have the boundary is essentially a purely 2-dimensional system, and this, for n greater than 2, we must have a finite correlation length. We can have neither true long-range order nor quasi-long-range order. So therefore, the phase diagram does not mandate the existence of separate ordinary and extraordinary regions. There is no phase like this. There is no extra phase above Tc, above the bulk Tc. So it's very conceivable that for all values of surface coupling K1, one just has a single universality, boundary universality class, the ordinary universality class. However, it's also not ruled out that the phase diagram looks like this, that you have at the bulk TC, you have several boundary universality classes depending on the value of the surface coupling K1. And these distinct boundary universality classes connect the same phases above and below bulk TC. There is kind of no theorem that tells you that this cannot happen, although this is kind of a much less minimal scenario than the one on the left. And in fact, if you look at the literature, I think people kind of implicitly always assumed that this is what happens, that you have just a single boundary universality class for all K1. So each one of these scenarios occurs. And I'll try to convince you that actually the answer depends on the value of n of the ON model. When n is large but finite, we have the situation on the left with just a single ordinary boundary universality class. On the other hand, now I'm going to treat n as formally as a continuous parameter, and I can show essentially rigorously that when n is just above 2, the phase diagram has this form, with distinct ordinary and extraordinary regions. And the extraordinary region is of the same character as for n equal 2, as for xy spins, that is the spin-spin correlation function on the boundary decays as a power of logarithm of separation. The only new element is that this exponent q now depends on n. What happens, of course, this is treating n as a continuous variable is kind of a formal device. Ultimately, we will be interested in what happens for integer values of n greater than 2, 3, 4, etc. And I will comment on that later. But first, where does this picture come from? Where do these two different regimes of n come from? What's the intuition? Let me first explain the intuition. Well, first the regime with large n. When n is large, one can turn the crank of large n calculations, standard large n calculations. And if you take n equal infinity, you find that you don't have a special fixed point in d equal 3. You only find an ordinary fixed point. And you can understand it also in the following way. You can take dimensions slightly larger than 3. Then the phase diagram looks like this. We discussed this. And you can track what happens to the special fixed point for large n as dimension approaches 3. And what you find is that the scaling dimension of the boundary order parameter at the special fixed point for large n and for d close to 3 has the following form. So this is calculation done by Ono and Akaba a long time ago. And you see that, well, we don't know what this 1 over n squared term looks like, but from the first two terms at least, it looks like for large n, as d approaches 3, the scaling dimension of the boundary order parameter at the special transition goes to 0. What does it mean scaling dimension is equal to 0? It means that you have long-range order. We have long-range order at the extraordinary transition. So it looks like the special fixed point is approaching the extraordinary fixed point as d goes to 3 when n is large. And maybe when d is equal to 3, they exactly collide and annihilate, so that you're just left with the ordinary fixed point in d equal 3 for large n. And this is indeed what my renormalization group calculation shows, as I'll discuss in a second. All right, so this is the regime of large n. What is the intuition in the regime when n is just slightly larger than 2? Well, we know that when n is equal to 2, we have 3 fixed points: ordinary, special, and extraordinary. We now running, kind of getting ahead of ourselves. We also know that this is extraordinary log, but doesn't matter for this purpose. What's important is that fixed points in a renormalization group don't just appear and disappear at will. They disappear by colliding with each other, and they appear in pairs. So these fixed points are all far away from each other. So they cannot immediately disappear when you make n slightly larger than 2. They have to survive for some range of n. So that's the intuition for this regime. Now let me support this intuition with some renormalization group calculations. Okay, so how do these renormalization group calculations go? We want to understand the region of the phase diagram where the surface coupling K1 is large. In this region, there is a strong tendency for the boundary to have at least a local order. So let me describe the boundary by a local order parameter n, that's going to be a unit vector, and write down a nonlinear sigma model for this boundary order parameter. And for a moment, let me imagine that the coupling of the boundary to the bulk is turned off. So we just have a pure boundary layer of strongly coupled spins. Let me remind you what happens in that case. Well, Polyakov taught us what happens to this two-dimensional sigma model. We have this renormalization group flow of the coupling constant G. 1 over G is essentially the inverse stiffness of the boundary. And well, what is this flow? This flow is towards G equal infinity. So if we start with a small coupling constant, it runs away to infinity. This is interpreted as the model acquiring a finite correlation length, right? There is the O3 model the ON model in 2 dimensions with n greater than 2 has a finite correlation length. Okay, well-known physics. Question we want to understand is how is this physics modified when we include the bulk, when we couple these boundary layer of spins to the bulk. And here I'll just tell you the answer. The answer is that you can still write down a renormalization group equation for this boundary coupling G, but it has essentially the same form as without the bulk, but the coefficient in front of G squared is modified. There is still this contribution from the boundary, same as what Polyakov taught us, but there is also now a contribution to the coefficient from the bulk. What is this S? S turns out to be a ratio of certain universal amplitudes at the normal fixed point. Remember, the normal fixed point is the one where you apply a symmetry breaking field on the boundary. And the normal fixed point exists in any dimension, so it will not matter very much precisely what this S is, but just suffices to say that it's a universal n-dependent number. All right. So what is the physics? Well, the physics crucially depends on the sign of this coefficient alpha. If alpha is positive, then G flows logarithmically to 0 in the infrared, and this is precisely the extraordinary log fixed point. If you integrate the RG equation along this flow, you find that the boundary, the correlation function of the boundary order parameter precisely has this decay with the exponent q expressed in terms of alpha. That's the extraordinary log physics. What about, well, if alpha is less than 0, then we know that the G equals 0 fixed point is unstable. G runs away from G equals 0. What is the fate of the system in this regime? We will discuss. We don't know precisely, but we will discuss some scenarios in a second. All right. Now we see, things crucially depend on the sign of alpha. So is alpha positive or negative? And for general n, we don't know, but there are certain limits where we do know the answer. First of all, when n is equal to 2, the bulk, the boundary contribution to alpha vanishes, and we just have this first term here. This first term is manifestly positive. So when n is equal to 2, alpha is positive, we have the extraordinary log universality class, it's stable. And we know that for n equal to 2, just by the topology of the phase diagram, there must be an extraordinary region, so that's good, that's reassuring. And we now know that that extraordinary region is of the extraordinary log character. What about when n is large? When n is large, one can actually explicitly calculate this this number s, and here is the answer that you get. You find that that alpha is negative, and in fact, one can also calculate 1 over n corrections to this number and get this n minus 4. Yes, Leo?
Yeah, I didn't quite understand the logic, because if alpha is positive, that just says you have an ordered state for the surface, because this RG is a surface RG.
It's not quite.
If I understand correctly. But then how do you? Oh, okay, coupling to the bulk.
It's not quite ordered, because G only flows to 0 logarithmically, and if you if you put in the anomalous dimension, which actually is not renormalized by the bulk, it turns out, and you integrate the RG equation, you find that that you accumulate this logarithm. So it's not quite. It's almost ordered, but not quite. But maybe that's not your question.
Sorry. So this flow, the flow that you have coupling to the bulk, the flow with the alpha, that's the flow of G in the bulk.
This is the modification due to the coupling to the bulk of the flow of this boundary coupling constant G. So I'm suppressing what the coupling to the bulk is. If you have time towards the end of the talk, I can show you how exactly these calculations are done. But the final answer is that this coupling constant G, even when we couple to the bulk, it makes sense, and its flow is modified by the coupling to the bulk, and it's modified in this manner.
Right. So I guess the point I'm missing is, so this describes the equations you have here. They describe how the surface, what happens above what you call an extraordinary transition. It describes the properties of the surface.
Yes.
And what I'm confused about is where's the information of how those log correlated power of a log correlated surface degrees of freedom impact the bulk transition?
Very good. Yeah, that's a great question. So remember I told you about the normal transition. That's a transition in the field. Mm-hmm. And I told you that when dimension D is greater than 3, the normal transition essentially coincides with the extraordinary.
Mm-hmm. Yes.
And that's essentially still true for the bulk correlation functions when D is equal to 3.
Is it because the decay is so slow? The surface degrees of freedom is so slow. It's only a log.
Well. So there's.
Oh, okay. G flows to 0. I see.
Right. So because G flows to 0, essentially, again, the boundary degrees of freedom decouple from.
They're basically their fluctuations are weak, essentially.
They're weak. That's right. So the bulk,
okay, that's a good. Okay, I just was looking for that intuition. Okay, thank you.
That's right. And now it turns out that if you think about the bulk, and like I said, the bulk is essentially described by the normal fixed point, but turns out this is only true in the limit where you scale both the coordinates perpendicular to the surface and along the surface in the same manner. If you take the opposite limit, where say you go into the bulk, but you separate the coordinates by a very large distance, then you recover this kind of log technique. So there are some subtleties to this statement.
Yeah. There's a scaling function with a ratio of x, x parallel and x perp or something like that. Yeah,
that's right. But for very large separation along the boundary, it actually crosses over from the normal form to a different
okay.
form. And that's a subtlety. Yeah, but great question. All right, so we were talking about this behavior of alpha when n is large, and like I said, you can calculate explicitly, and here is the result that you get. So you find that alpha has to change sign as n increases from 2 to infinity. And well, alpha is a continuous function of n, we expect, so we expect there has to be a zero somewhere at some critical value of n equal to nc, and nc has to be greater than 2. So there exists a finite region where the extraordinary log phase exists and is stable, n between 2 and nc. So what is nc? That's kind of the most interesting question, perhaps. Well, if you just take this large n estimate and extrapolate it down to moderate values of n, you find that nc is somewhere around 4. How accurate this estimate is, we don't know. I would like to actually advertise some work that's going to appear hopefully soon. Some work with Ilya Grusberg, his graduate student Jay Padayasi, Marco Meneri, who is a postdoc in Lausanne, and Abhijit Krishnan, who is graduate student at MIT. And this work actually uses conformal bootstrap to compute alpha. And under certain set of assumptions, we're actually able to rigorously show that nc is greater than 3. So 3 is in this, according to this work, is in the extraordinary log phase, which is kind of means that this region does contain some integer values of n, some physical values of n. All right. So very good. Now, next question is, what is the evolution of the phase diagram past this n equal to nc? Well, when n is close to nc, this coefficient alpha is small. So really, the physics is going to be determined by the next terms in the beta function. And so near n equal to nc, I can linearize the coefficient of the first term, the g squared term, and then there is also some high order term, some g cubed term. And the physics is really going to be determined by the sign of this coefficient b. So we have to consider both, we don't know actually what the sign is, so we have to consider both possibilities. If the sign is positive, then what happens is for n just below nc, when you look at the RG equation, you find an infrared unstable fixed point at the perturbatively accessible value of g. And you can calculate all the critical properties at this fixed point. The scaling dimension of the order parameter, of the boundary order parameter, becomes small at this fixed point. What is this infrared unstable fixed point? Well, natural guess that it's the special transition. We know that when n is equal to 2, there is a special transition between the extraordinary log and the ordinary regimes. So the natural guess is that this line of special transitions just continues between n equal to and n equal nc, and when n is equal to nc, it collides with the extraordinary log fixed point, and then they annihilate for n greater than nc, such that only the ordinary boundary universality class is left for n greater than nc. So this is the simplest scenario. Second scenario is that this coefficient is negative. In this scenario, the special transition survives for some range of n above nc, and the extraordinary transition also survives, but it changes its character. For in this scenario, for n slightly larger than nc, we find that the extraordinary fixed point moves away from g equals 0 to a finite value of g. Again, kind of perturbatively accessible, but finite value of g. And we get a infrared stable fixed point at this small value of g. And we refer to this as the extraordinary power universality class. So here, really, the boundary correlation function will decay in a power law manner, not in this logarithmic manner, but really true power law. This will be a true boundary conformal fixed point. So this is what happens for n just slightly larger than nc, and well, we know that when n is equal to infinity, only the ordinary universality class is left. So the natural guess is that for larger n, eventually the extraordinary power fixed point collides with the special fixed point, and the two annihilate at some larger critical value n equal to nc2. So here is another way to look at the phase diagram in the two scenarios. Here is scenario 1, where the special transition just as we approach nc occurs at larger and larger value of kappa, and well, eventually disappears for n greater than nc. And here is scenario 2, where the extraordinary fixed point evolves into the extraordinary power fixed point when n is in this range here. Scenario 2 is kind of more involved than scenario 1, but because we don't know what the sign of B is at the moment, we kind of have to consider both. All right. So this is everything that we know analytically at this point, and really the rest has to be settled with numerics. And let me remind you, the open questions are: what is the value of nc, and which of these two scenarios is realized? So in the remaining time, let me tell you about current understanding from numerics, from Monte Carlo. And let me begin with numerics on classical models, just classical ON model. And if I have time later, I'll also talk about the quantum models. So actually, there was, until my paper appeared, there was very little numerical work on this problem. I could find only two classical Monte Carlo studies for n equal to 3. So we know, theoretically, we kind of already know what happens for n equal to 2. So the next interesting value is n is equal to 3. And here is, okay, so here is classical Monte Carlo on O3 model. And this paper by Crack actually, well, essentially couldn't tell what happens for large values of the surface coupling. It couldn't quite make out what the system crosses over to. And this subsequent paper by Deng, Blot, and Nightingale, which I already have mentioned, they saw actually a hint of a special transition for n equal to 3. So what's plotted here is the Binder ratio associated with the surface order parameter, and there's a crossing point in this Binder ratio as a function of the surface coupling, and what's plotted is different system sizes. So this is kind of standard way that you look for a phase transition. You look at the Binder ratio and you look for a crossing point. And here they seem to find a crossing point at a finite value of surface enhancement kappa that they thought might be a sign of a special transition. they were not able to determine the character of the phase with large kappa, of the putative extraordinary phase. So this was all we kind of knew from classical Monte Carlo when my paper came out. But there have been one more data point. There was actually also a study for n equal to 4 by Deng. What he saw for n equal to 4 is quite similar to what was also seen for n equal to 3. So again, there is a crossing point in the Binder ratio of the surface order parameter. Again, he couldn't determine what the nature of the high kappa surface phase is. All right. Now, since my paper came out, there have been a number of large-scale, high-quality Monte Carlo studies, and here is one by Francesca Toldin, so he studied the classical O3 model, and again he observes a crossing point in the surface Binder ratio as a function of system size and surface coupling, and he was able to extract so he interprets this as a special transition, and he was able to extract the critical exponents, the surface critical exponents associated with this special transition, the scaling dimension of the surface order parameter, and the correlation length exponent. Francesco also investigated the large kappa regime of the phase diagram, and his findings appear to be consistent with the extraordinary log universality class. So here is, for instance, the 2-point function of the surface order parameter, and you see it has a very slow decay that appears consistent with logarithmic decay of this form. Perhaps even more interesting is this stiffness of the system. So for a true conformal fixed point, boundary conformal fixed point, this expression L times the stiffness should approach a constant. Whereas for the extraordinary log phase, it should grow logarithmically with system size. Essentially, the stiffness of the system in the extraordinary log regime is going to be dominated by the stiffness of the boundary, and we know that the stiffness of the boundary is essentially 1 over the coupling constant of the boundary, and we said that this coupling constant flows to 0 logarithmically, so we expect that the stiffness grows logarithmically. And we see, first of all, in numerics that the stiffness does not saturate, even for very large system sizes. I think the largest system size here is around L equal 400. And it does seem to be roughly consistent with logarithmic growth. And from these two observables, one can extract the coefficient alpha. Remember, Q is also related to alpha, and Francesco finds it to be in this range. All right. So it seems from Francesco's numerics that n equal to 3 is below nc, that there is an extraordinary log phase, an ordinary phase, and a special transition between them for n equal to 3. That's quite exciting. All right. Now, there was also a detailed classical Monte Carlo study of the n equal to 2 model in the large kappa regime, in the large surface enhancement regime. And again, it found results consistent with the extraordinary log phase at large kappa. So here is again the 2-point function, seems to decay as a power of logarithm. The power seems to be the same, independent of where in the extraordinary log phase one sits. Here's the stiffness. Again, it seems to grow logarithmically, and the exponent extracted from the stiffness and the coefficient alpha extracted from the stiffness seems to match the coefficient extracted from this power Q. Remember, they're related like this, and the power, the value is quoted here. All right, so again, things seem to be consistent with the extraordinary log universality class for large kappa and n equal to 2. Okay, now so here's by the way the kind of compilation of values of alpha for the two values of n that have been studied, and you see that alpha decreases as n is increased. Well, that's consistent with our picture. Remember, alpha has to change sign as n passes nc, and we see that alpha initially decreases. All right. Now, which of these two scenarios do we have for the evolution of the phase diagram? Is it the one on the left or the one on the right? And we don't know yet for sure, but if I had to bet at this point, I would say that it's the one on the left. Why? Well, remember, for this scenario, for this first scenario, the special transition approaches the extraordinary log fixed point as n goes to nc and annihilates with it at nc. And in particular, as n approaches nc, the scaling dimension of the boundary order parameter and the inverse correlation length and the inverse of the correlation length exponent at the special transition becomes small. And well, here is a compilation of that data at the special transition as a function of n, and you see that both actually decrease as n is increased. And if you look at this paper for n equal to 4 by Deng from 2006, they actually become quite small when n is equal to 4. Although probably the error bars on this is also quite large when n is equal to 4. But so far this seems to be consistent with first scenario for the evolution of the phase diagram, and critical value of n somewhere not far from 4. Okay, so this is all the classical Monte Carlo data that I'm going to discuss. Now, how am I doing for time?
So you are at -5 minutes, but just feel free.
But there are still some 10 minutes for questions.
Yeah, we can go ahead. Yeah.
I mean, I don't know. I mean, I was going to discuss some quantum models too, but let's see what the attendance is like. Yeah, let me very quickly maybe go through these quantum models.
Okay.
So far I focused on classical models, but one can also consider quantum spin models in 2 dimensions. Actually, a class of these models have been studied with quantum Monte Carlo in the last 5 years or so, and they actually studied different geometries, but kind of prototypically they're all more or less similar to the following model. So consider a 2-dimensional rectangular lattice of spins with nearest neighbor couplings that are dimerized like this. So the red bonds have stronger couplings JD, and the black bonds have weaker coupling J. And then in the bulk, this model has a phase transition from a paramagnetic phase at a large ratio of JD over J, where the spins on red bonds just lock into singlets, to a Néel phase at JD over J equal to 1, where we just have a square lattice Heisenberg antiferromagnet that we know orders in a Néel pattern. And this phase transition numerically is well confirmed in the bulk to be of the O3 universality class. So this goes back quite a while. The recent studies focused on the boundary universality in this model. And one can actually study 2 different types of boundaries. One is so-called non-dangling boundary, where the boundary spins are part of these strong red bonds. And then there is another kind of boundary people have considered, which is a dangling boundary, where the spins are part of the weak black bonds. And when these boundaries were studied at the bulk critical point, what was found was that for the non-dangling boundary, the scaling dimension of the boundary order parameter is quite close to that for the ordinary universality class of the classical O3 model. But for the dangling boundary, the scaling dimension was very different. And in fact, roughly the same scaling dimension was seen in a number of microscopic models for the dangling edge. And the first thought that people had was, oh, this has to do with kind of SPT physics. Remember, in the beginning of my talk, I said that if you drive an SPT, a symmetry-protected topological phase, to a phase transition, something of the edge state can remain. Now, if you go into the paramagnetic phase here, you can, when spins are spin 1/2 spins, you can think of it as a kind of weak SPT. You can think about each one of these columns as a kind of Haldane chain with a dangling spin 1/2 on the edge, and then, in the paramagnetic phase again, the spin 1/2s, they form a Heisenberg chain. So you expect already in the paramagnet the boundary, the dangling edge, to be gapless. And then you kind of ask what happens to this gapless dangling edge as you approach the bulk transition. So this is exactly the kind of question that I mentioned in one of my introductory slides. The problem is that, and then of course you don't expect the ordinary universality class in this case, because, for the ordinary universality class, if you go into the paramagnetic phase, the boundary has a finite correlation length, whereas here it would be gapless already in the paramagnetic phase. But the big surprise, at least for me, was that people then also studied same kind of model, but with spin 1, where you don't expect this gapless Heisenberg chain on the edge. Spin 1 chain is gapped, so you expect the paramagnetic phase to have a gapped boundary. Nevertheless, at the bulk critical point, the scaling dimension of the boundary or the parameter at the dangling edge was almost the same as in the spin 1/2 model. So how to explain this? And I think the one explanation that one might propose at the present point, and which was actually proposed earlier in a number of papers, is that perhaps in this model the dangling edge is controlled by the special transition. So we know that in the classical O3 model there is a special transition between the extraordinary log phase and the ordinary phase for n equal to 3, and the scaling dimension of the special transition, as extracted by Francesca Toldin, is something like this, 0.26. Well, looks quite close to what is found at the dangling edge. The mystery is that why is this dangling edge at the special transition? Because for the special transition, you have to tune the boundary coupling to be at the special transition. It's an infrared unstable fixed point. Whereas here, no tuning was performed on the edge, and in fact, the same exponent was seen in a number of microscopic models without fine tuning. So what's going on? And I think the answer is not clear. Perhaps one thought is that the correlation length exponent is quite large at the special transition in the O3 model. So then, if you somehow accidentally start close to the special transition, it takes a long time to flow away into one of the one of the stable boundary phases. But still, I think this is quite mysterious. So I will not talk about differences between spin 1/2 and spin 1. And let me just conclude by saying that, well, the old textbook ON classical model still holds surprises as far as boundary criticality is concerned. I hope this will motivate more Monte Carlo work, both on classical and quantum models. I think for both there are still open questions, and I think some progress can be made also with conformal bootstrap. Yeah, so let me stop here, and thank you for your attention.
Oh, thank you, Max, for this very interesting talk. So any questions from the audience? Oh, Leo, please go ahead.
Yeah, I just had a question about the classical ON model criticality, about criticality. Just about pointing out that there's many boundary theories.
Leo, I think you're freezing.
The conditions for the classical model of your results. So for what boundary conditions is this done, or is it boundary condition independent? I would think it's very strongly dependent on the boundary conditions.
Sorry,
Yeah,
Leo,
so
lost you for a sec, I guess. Max, did you hear the question? I think we lost him for a second.
Leo, maybe you can repeat your question because you froze for
Sorry if my internet is weak and if can't understand the question, then feel free to ignore. I was asking about the boundary conditions, how the boundary for the classical ON model. You seem to have not said anything about boundary conditions.
Yeah, so I mean, this is a UV definition of the model on the lattice, right? And then you can think about the boundary condition. What sets the boundary condition is this ratio of the surface coupling K1 to the bulk coupling K. If you want to do it in a field, if you want to do it in a field theory, you also can, right? You can write down a phi to the 4th field theory in the bulk, and on the boundary there is going to be a term like C phi squared.
C phi squared. Okay.
And then you can tune this C to be large and positive or large and negative. And those will correspond respectively to the large. The large negative C is one where the boundary has a strong tendency to local order. That's kind of the same as the large kappa side of this diagram. And then the C large and positive, that's phi is suppressed on the boundary. That's the ordinary class. And then you can tune between them. When you go to if you work in the 4 minus epsilon expansion, then this is exactly the formalism that is useful. And in fact, C equal infinity is the Dirichlet boundary condition, C equals 0 is the Neumann, and C going to minus infinity is the extraordinary phase where the boundary actually has order. When you talk about it, when D is equal to 3 and fluctuations on the boundary are very strong, and also the bulk is strongly coupled, or fairly strongly coupled, this formalism turns out to be not very useful. But if you want to kind of define the model in the UV, you can like this. Yes.
Okay. Thank you.
Any other questions? So I have one then super naive question. So do vortices play any role in this story with the boundary and everything?
Very very good question. I don't know if I have slides on it. It's also related to this last to this last footnote here. So vortices, kind of the most natural place for them is for n equal to 2.
Right.
And so maybe let's go back to the phase diagram for n equal to 2. This may be good enough. Right, so I said that for n equal to 2, the Kostelis-Thouless transition, this green line is the Kostelis-Thouless transition, so of course that's driven by vortices.
Mm-hmm.
Now you can ask, okay, what is the fate of vortices for this extraordinary log transition? And you expect that they are irrelevant at the extraordinary log transition. Because remember, the stiffness diverges at the extraordinary log transition, so the vortices, the scaling dimension of the vortices we expect to go to infinity. Now what about at the special transition? Do vortices play a role? And it turns out that if you consider a classical model, then they do. We cannot understand the special transition without including vortices. If you consider quantum models, then by tuning the boundary density, the boundary boson density, you can actually suppress vortices. You can make vortices prohibited by translational symmetry. And then in that case, you can actually understand the special transition exactly. You can have a theory for the special transition. But for the classical model, vortices do play a role at the special transition. And for other values of n, for n equal to 3, the role of kind of what's similar to vortices is skyrmions, and you have the theta term, and that's related to this difference in physics for s equal 1/2, s equal 1/2 and s equal to 1. And yeah, there is some story there too, but I will not get into it.
Okay, thanks.
Mm-hmm.
I don't see any other hands. So at this point, Val, I would like to thank both speakers for the wonderful talks, and this concludes the conference. And thank you for all the participants as well, and keeping it lively. And see you in the next meeting. Thank you all.